So this in this talk, I would like to focus on pure physics, and I would like to go back to the roots of physics itself. So before the real talk starts, I would like first to do a little detour of what are the cornerstone of physics itself. So how do we describe the universe itself? Yeah. So we have so there are two main branches of physics. So on the one hand, you have quantum field theory and the standard model of particle physics. So this is based on quantum mechanics itself, but with the additional incorporation of special relativity. Yeah. And then on the other hand, we have general relativity, which is a pure classical theory, which we use to describe gravity, also at large scales. So, for example, it predicts objects like black holes and so on. Now, on the one hand, you can quantize, you can treat these three of the four fundamental forces, namely electromagnetism, the weak interaction, and the strong interaction. You can treat it perturbatively. So you can compute quantum amplitudes in terms of a series expansion, and you can represent that graphically in terms of these diagrams, which are called Feynman diagrams. But on the other hand, this cannot be done for gravity itself. This was shown in 1986 by Gorov and Sagnotti. So they showed that as soon as one goes to higher loops, so if one considers higher diagrams with more loops, at second loop there are some divergences which cannot be absorbed into counter terms. Yeah, so it's impossible to get rid of these divergences. This was not the case for electromagnetism and so on, which worked perfectly. So it seems that so far our best description of gravity itself is classical, yeah, and it's given by the Einstein field equations. Yeah, so this here we have the Einstein equations themselves, which are written in terms of so G mu nu is the metric of space-time, R mu nu are some other additional tensor which are constructed in terms of the metric itself. T mu nu is the stress energy tensor, which takes into account how much matter or radiation we have there. And okay, so then how do we quantize gravity? So we cannot use Feynman diagrams for gravity. So the question is, how do we achieve this final theory of quantum gravity? Of course, the goal is very ambitious, but there is a simple idea. So now, since the Einstein equations are nonlinear, right, because of their structures, then one can say, okay, maybe the final theory of quantum gravity will involve also some nonlinear modifications of quantum mechanics as well. And this was the main idea behind this work. So the idea is to apply methods which are commonly used in quantum information theory to dismiss or to rule out some specific nonlinear modifications of quantum theory. So you cannot choose which is the right one, but the best you can do is to rule out some of them. So you know at least, okay, at least I know that this cannot be the right one. Yeah, and this is the content of this paper. So this was a work done in collaboration with my colleague Martin Plavola. This is still on archive. It has not been published yet, but it's still on archive with this title. So then now we can finally start the main talk. So first, I will talk about the concept of contextuality and the Cohen-Specker theorem. And then I will discuss generalization of that, which was done by Speckens 20 years ago. Thirdly, I will discuss some famous nonlinear modifications of quantum mechanics, which were already discussed in the literature so far. Okay, so then what is contextuality? Because I said we will use contextuality to rule out some nonlinear modifications of quantum theory itself. So it's first better to define what contextuality or non-contextuality is. So this comes. So this concept goes back to the very early times of quantum mechanics. So there is a famous quote by Einstein, which says that where he says that God does not play dice. So This is the original letter he wrote to Born in 1926. He says that quantum mechanics is a very respectable theory, but he still thinks that there is something more behind that. And he says that for that reason, he says that God does not play dice. So he was saying that he was thinking that maybe it is possible in principle to achieve the same results that quantum mechanics does, because maybe there exists a classical theory made of hidden variable that can replicate the prediction of quantum theory. So then how we arrive to the concept of non-contextual hidden variable model for quantum theory, which basically, so the definition is the following. So you can make a measurement of some Hermitian operator, and if the outcome of this measurement is depends only on that Hermitian operator, but not on which other operators you are measure simultaneously with that, then you say that you are that your theory is non-contextual. So then in the 60s, there was people studied this, and we have a famous result, which goes under the name of Kochen-Specker theorem. So the Kochen-Specker theorem basically rules out non-contextual hidden variable models for quantum theory. So basically, it says that quantum mechanics itself is contextual. Yeah. So another way to express this is that measurements in quantum theory cannot be considered as revealing pre-existing values of a specific classical hidden variable. So this was the original Kochen-Specker formalism for contextuality. And this traditional definition has some problems, or it's at least lacking in certain respects. So for example, it is strictly specific to quantum mechanics only. It applies only to deterministic hidden variables models, and it does not extend to unsharp measurements. So the original theorem only involved sharp measurements, so these given by projective operators. But one can wonder what happens if we allow for unsharp measurements given by these POVMs. So this, motivated by these questions, in 2005, Speckens proposed a new definition of a non-contextual ontological model for a general operational theory. So not necessarily quantum theory, but more broadly, you can consider a general operational theory. So how does he define that? So in an operational interpretation of a physical theory, you can select some primitive elements, which are preparation procedures. So how can you prepare, for example, a state? A transformation procedure, how do you transform a state? And a measurement procedure, so how do you, at the end, measure the states? And the final role of such a theory is to specify the probabilities for different outcomes. Yeah. So the best you can do is to compute the probability for an outcome K that results from a measurement procedure M, given a preparation procedure P, and given a transformation procedure T. There is also a notion of equivalence. So we say that two preparation procedures are equivalent if they give the same long-run statistics for every possible measurement procedure. We say that two measurement procedures are equivalent if they yield the same long-run statistics for every possible preparation procedure. And so we identify equivalence classes. Yeah. So with that in mind, we can distinguish two types of features for an experimental procedure. So a feature that is specified by also specifying the equivalence class that the procedure falls in. Or on the other hand, you can have a feature that is not specified by specifying the equivalence class. And the set of features of the second type forms the so-called context of the experimental procedure. Another definition that Speckens provides is what is an ontological model of an operational theory. So one assumes that there exist physical systems which are the subject of our experiments, and that they have some attributes regardless of what anyone knows about them. Yeah. So at a given time, we can fix an ontic state of the system. If the ontic state is not completely specified after specifying the preparation procedure, then one would need some additional variables to specify it, and these are called hidden variables. So now if one knows that the system was prepared using a preparation procedure P, one can describe the system by a probability density mu over the variable, the hidden variables. So now for every value of lambda, one can associate the probability zeta of obtaining an outcome k in a measurement m, given that the system is in the ontic state lambda. So an ontological model of an operational theory where the representation of every experimental procedure depends only on its equivalence class and not on its context is called then non-contextual. Yeah, so this is the general definition, but we can be more precise. We can give an explicit formula for that, which we will use for explicit calculations. So first one says that an ontological model is preparation non-contextual if the representation of every preparation procedure is independent of the context. So if this formula holds. Analogously, you can say that the measurement, the ontological model is measurement non-contextual if the representation of every measurement procedure is independent of the context. So if this holds. And finally, you can say that it is universally non-contextual if it's non-contextual for all experimental procedures. Yeah, so with this in mind, one has, so the basic ingredient is then a preparation procedure P and a measurement procedure M. Then one can compute the probability to an outcome K with this formula. So one integrates over the probability of lambda times the probability assigned to outcome K given lambda. Yeah, so this is the Speckens prescription for computing these probabilities. Yeah, so we have a very explicit formula. So for Kochen-Specker contextuality, you didn't have such a formula, but here for Speckens, you have a very explicit formula. Yeah, which this holds for a generic operational theory, but then we would like to specify this formula for quantum mechanics itself. Yeah, so we ask how does the formula look like for quantum theory? Okay, so then for quantum theory itself, as I said, the preparation equivalence classes are described as quantum states. So here in this talk, I usually use the convention where when I say state, I actually refer to density metrics. Yeah, so states will be then these positive semi-definite unit trace linear operators, while measurement are either projective operators or, as I said, you can be more general. You can have positive operator valued measures, which they do not have to be projectors, but they just have only one constraint, which is they sum to 1. So now we arrive to the formal definition of Speckens non-contextuality for quantum states. So if you can write down the probability for an outcome K given a measurement M for these states rho I in this way, so as a sum over these coefficients lambda with a trace of rho I g lambda times the trace of sigma lambda mk for every state and for every measurement, then you say that this set of states is Speckens non-contextual. And these sigma, they are quantum states, and these g lambda, they are so-called pseudo-PUVM, so they don't even have to be positive semi-definite. Yeah, so here we have a very precise definition. So either you satisfy this formula or you do not satisfy this formula. So either you find the sigma and g, or you do not find them. Yeah, so in some sense, this notion of Speckens contextuality gives you a yes or no, is a Boolean property. You are either contextual or you are not contextual, given some fixed states rho. So in this paper, we proved a theorem. So this theorem gives you necessary and sufficient conditions for a set of states to be Speckens non-contextual. So this holds only for pure states, actually. So pure states are spectrums non-contextual if and only if the states are linearly independent. So we can quickly go through this theorem since it's very important. So the proof is by contradiction. So you assume that the states are linearly dependent and non-contextual. So by definition, you could find this sigma and g. So you can equate these two traces. But now you know that when you have an equation like that, then the states are the same. So you can write your rho in terms of this sum. The second step is to define a map in this way. So a map which takes as input as states and outputs tensor product of states. Now this map is particular because when you take the partial trace either over the first subsystem or the second one, you always get rho, which we know it's pure. So then we use the result that when this happens, this means that the initial state must be made of pure states themselves. So since this holds for both trace over A and B, then we can conclude that theta is a tensor product of these pure states rho I. And finally, if the states are linearly dependent, then we know that the definition of linear dependence, so this holds, we can find non-zero alpha such that this is true. So we can write down one specific rho k, and then you can act on theta on this rho k. So first you can use theta rho k acting on this explicit form, or you can go back and use the theta rho k given by this definition. So you have two possibilities. They are the same object, so you have to make an equal sign here in between. But then if you expand both sides, you see at the end that there is a contradiction. So either we see that either all states or rho k are zero, but this does not make sense because rho are states, so they cannot be just zero. Or the two of them are the same, but this is also a contradiction because we know that we started from the beginning with a set of different states. So this was the main idea behind this theorem. So now the main idea of the paper itself is to first consider some pure and linearly dependent and hence contextual states because of our theorem. Then you let the states evolve according to some nonlinear model. Many nonlinear models which were studied in the literature, they predict that the states become linearly independent. So they will become non-contextual. So there is a graphical description of that. So one can consider these states, so 0, 1, phi of 0, and psi at time 0. They all lie, you can select states which initially lie on the same plane. But then what happens when you do a nonlinear transformation is that those states will move along the Bloch sphere with different speeds. So at the end, those states will lie on different planes. And that's why at the end we will have states which are linearly independent, even though we started with linearly dependent ones. So at the end, you create an experiment and you measure experimentally if the final states are non-contextual, as the theory expects. But if you see a contradiction, so if they remain contextual, then they also violate some non-contextuality inequalities. Yeah, and in that case, the model can be ruled out. Yeah, so so the idea is very simple. You check experimentally if the states behaves according to theory. Yeah, so if this is not the case, then it means that the model cannot be right. So you can rule it out. If they behave according to theory, then you cannot say anything because it just says that the model can be in principle correct. But of course, you do not know if this is the final one, the best one. So with this idea, you can only rule out stuff, but you cannot claim that what the final right theory is. And then, so in the paper, we analyze some examples of nonlinear modifications, which were analyzed already in some previous works. A very simple example goes from Deutsch. From a paper from 1991, he considered a very somehow also artificial example because this is just a map which takes rho and just takes a tensor product of that. So this is not even related to gravity itself. It's just some not necessarily related to gravity itself. It's just some, if you want, some toy example. but also very simple to analyze because you can consider, for example, these first initial states, the 0, the 1, the plus, and the minus. So the one which makes, so 0 and 1 are the computation, the basis, the computational basis. The plus is the 0 plus 1 divided by the square root of 2 and so on. Then you take this tensor product. So from 2 times 2 matrices, you get 4 times 4 matrices, which you can check they are become linearly independent. Yeah. So the Deutsch map maps linearly dependent pure states to linearly independent states. Another example, a little bit more fancy, is the Weinberg's model. This was proposed by Weinberg in 1989. So instead, he says that, okay, instead of considering the Schrödinger equation itself, maybe I can consider this new equation, where for psi chi, so this psi chi is just the projection of the state on one component. And so you can start with a generic qubit, which can always be, as you know, can always be written in terms of angles theta and phi. And then one can show that this qubit is mapped to, after some time t, to this new expression where there is this additional phase. There is this additional omega of theta, an additional phase which depends on the angle of theta. Yeah. And then if you then consider, if you assume that the initial states were linearly dependent, then because of this expression, then you can, if you do explicitly the calculations, you can show that they are, you can convince yourself that they become linearly independent. Yeah. So here again, we see this behavior that from linearly dependent pure states, you get linearly independent ones. And finally, we have maybe the most related to gravity itself that we have so far. So this Schrödinger-Newton equation, it was proposed by Yossi and Penrose to explain some gravity-driven collapse of the quantum mechanical wave function. So basically, Penrose, the idea of Penrose was that the collapse of the wave function is driven by gravity itself. It's not a matter of me that I observe the state. Yeah, so for a spin 1/2 particle which moves through a magnetic field, an initial state, alpha beta, will be mapped to this new state with 2 different components, where these components obey the Schrödinger-Newton equation, which is given by this formula. Yeah? So this F is just the gravitational force, the Newtonian one, so mg, plus the magnetic force. And then, well, here we have some new terms. So this rho is the mass density of the particle. So this is just modification of Schrödinger itself with these additional terms. Now, of course, this equation is very difficult to solve it analytically. So the best that one can do is to solve it recursively. So you first assume that these u are not there, and then you solve the equation without the u. Then you plug the solution and you put it back into the equation, and so on. Yeah. And then with this recursive approximation, you can show that, again, contextual states are mapped to non-contextual ones. So this behavior appears also for the Schrödinger-Newton equation itself. Yeah. So then we are in this situation. So we can pick up this, for example, these 3 models that we have. We can prepare some pure states which are linearly dependent and hence contextual. Then we let them evolve, and we assume that one of these theory makes the evolution. And then at the end, we experimentally measure again the contextuality of these states. Yeah. If we see that these states now are non-contextual, if we see that they are contextual, then it means that they do not satisfy the prediction of the theory, so we can rule out the model. But as I said, if they are non-contextual, they satisfy the model, but we cannot say anything because any model can be then right. Yeah. Exactly. So these are what I have just said. So we have proved a necessary and sufficient condition for spectrum contextuality, which works only for pure states. We have shown that nonlinear dynamics has the ability to map contextual sets of states to non-contextual ones. And the results, as I said, can be used to construct experiments, experimental tests of this nonlinear modification of quantum theory. Of course, then there are also some open questions. So, of course, here I didn't say how one does explicitly construct the experiment. So one has also to think, how do I actually carry out these experiments? Which experiments are best suited to test such nonlinear modifications? And then also we have this the question if Specken's contextuality itself is an absolute concept. But it seems that this is not the case, at least if you restrict to the spin degrees of freedom of a particle only. Yeah? And if you do this, then it seems that Specken's contextuality becomes a frame-dependent notion. So whether a state is Specken's contextual or not depend on which frame you are in. So this is which does not make very sense, because then I can be my frame and I can measure a contextual set of states, but then my friend is moving also with a very slow speed near me, and then she measures Specken's non-contextual states. So we would not be able to agree. Yeah. So if one restricts oneself to the spin degrees of freedom of the particle, then you find these contradictions, that the formalism itself is not well defined because it becomes a frame-dependent notion. Yeah. So it seems that one is forced to consider both degrees of freedom. So you have to consider both spin and momentum. So you cannot separate both of them. And this will be the content of the next paper of mine, which is not there on arXiv, but I think it will be on the arXiv in a few weeks or so. And with that, I conclude, and I thank you for your attention.